Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my pleasure to introduce TOMASZ, the co-organizer of this seminar. And he will continue the talk which I was giving. Now he will concentrate, he'll focus on another aspect of our work, which is about multiplicative structure for K-theory of non-commutative sister algebras. Tomek, the Zoom is yours, take it away.
Thank you for your introduction. So you see the title of my talk. I will focus on some aspects of K-theory, which are present in the classical setting, but up to my knowledge, it is something new in non-commutative topology. So what is this? Non-commutative topology, okay. So first of all, what is non-commutative topology? I will explain it in a minute. Why KK theory, which is the main tool in this subject, is not enough. Next, I'm going to explain what is this multiplicative K-theory from the title of sister algebras, not necessarily commutative ones. Then I'll define quantum CW complexes and show some application of all this machinery. Okay, so the present state of the art of non-commutative topology is based on Kasparov's KK theory. And this theory has many relatives in mathematics, since it has very general structure. First of all, it's a triangularistic category whose objects are separable sister algebras. And the two graded K-theory groups of sister algebras is a functor from this theory, okay? So therefore, it's an analog of other bivariant theories known in topology and geometry. First of all, the category of motifs in algebraic geometry, and the category of suspension spectra in stable homotopy theory. When restricted to metrizable locally compact Hausdorff spaces, after reversing arrows, these can be regarded also as a bivariant theory of spaces, metrizable locally compact spaces, Hausdorff spaces, and then it can be compared with some other theories.
Sorry, could you say in a few words how to think about this category of motifs? And I know this term, but I do not know how to think about them.
So the category of motifs was envisioned by Alexander Grothendieck, and next, at least partially realized by other mathematicians, to speak about universal kind of cohomology theory for algebraic varieties in such a way that whatever is possible on the algebraic level of this invariant of some cohomology theory already can be done on the level of algebraic varieties. The price for this construction is this, that you have to speak not about morphisms of varieties, you have to allow some generalized morphisms, which are correspondences. And correspondences appear in many other versions of this idea, for instance, in KK theory. So morphism in KK theory can be regarded as some generalized correspondences. So homomorphism of the star homomorphism between sister algebras are not enough. These generalized morphisms contain, for instance, Morita equivalences, which are not homomorphisms between algebras themselves, and they contain even more some correspondences which can be defined in terms of Fredholm modules and the representations of some algebras on Fredholm modules over some other algebras.
And sorry, just let me ask, it was finally realized, or it is something which is not realized?
Up to some, Grothendieck's dream was very far-reaching, but some versions, some restricted versions of this main idea was done. So now we can speak about category of motifs, at least for smooth varieties. Okay, but this is not a lecture about algebraic geometry. It's only an analogy. Okay, so all these theories are relatives, but because they satisfy these 3 points, but these are different categories, different even subjects in mathematics. So what is important in this comparison is that all these theories are based on the same main idea. Okay.
This analogy is not about the universality, but in this notion of morphism being something like a correspondence.
First of all, they are triangulated categories. Objects depend on your subject of choice. And invariance, important invariance got from this approach is a functor on this category. Usually it's a homological or cohomological functor, okay, on this triangulated category. So this is the main motif in mathematics, okay? Thank you for the parenthesis. Good. What is important about all these theorems? So first of all, for instance, in stable homotopy theory, stable homotopy equivalences do not recognize plane homotopy type, because spaces are replaced by so-called suspension spectra, when instead of a given space, you have to consider a collection of multiple suspensions of a given space. So it is more or less clear that in this way you are killing some properties of a given homotopy type of an initial space. For example, something which was connected can be disconnected. Sorry, another way around. If you start from something disconnected, then taking sufficiently many suspensions, you can make it connect. Okay, and I'm not talking about connectedness on the 0th level. Sometimes people are speaking about connectedness with regard to some higher homotopy groups. So the only thing which survives is the information about homotopy groups up to sufficiently many suspensions. Okay, so KK equivalences also suffer the same the same feature, because they also do not recognize different homotopy types of different spaces. We have even a theorem which in non-commutative setting was proved by Rosenberg and Choquette, and by this restriction to metrizable compact Hausdorff spaces, it means that if it is enough for a given two compact Hausdorff spaces, it is enough to have abstractly isomorphic K groups to be already KK equivalent. So this means that KK theory remembers about classical spaces very little. For instance, if you consider the complex projective space and the space consisting of n+1 points, then K theory of these two completely different spaces are the same. So they are KK equivalent. Although CPN is connected, but this space consisting of n+1 points is, of course, discrete, disconnected. But the K groups are isomorphic. So the problem is that classically, K theory is a much richer invariant than in the setting of sister algebras. Namely, they are not only abelian groups, they are rings. And these ring structures of this K theoretical invariants help a lot. Why in the classical situation this multiplicative structure is indispensable? So if we consider classical spaces up to morphisms which induce isomorphisms on K theory, then such morphisms induce already maps of K theory rings of these spaces. So you do not have to assume that your isomorphism of invariants is compatible with this additional multiplicative structure, because if this isomorphism is generated by or implemented by a map between spaces, preserving this multiplicative structure is for free. Okay. So therefore, speaking about at least metrizable compact Hausdorff spaces, we can speak about their equivalences to mean multiplicative K equivalences. Okay. But of course, we cannot do the same in the non-commutative setting, because
Tomasz, can you explain again why you need metrizable?
Metrizable for having corresponding sister algebra separate.
Okay.
Okay. Because Kasparov's KK theory behaves well for separable sister algebras.
Okay. Mm-hmm.
Okay. Okay. So the problem in the non-commutative setting is that in this approach, we do not have diagonals. In the classical situation, the diagonal map for a given topological space is dual to something which on the level of algebras corresponds to the multiplication in the algebra. And the multiplication of the algebra is an algebra map if and only if a given algebra is commutative. So if we allow non-commutative spaces, then we do not have a morphism corresponding to the diagonal. Therefore, it cannot induce anything on such invariants like K theory, for instance. So this relationship between multiplicative invariants and the notion of the diagonal map is very general. In many examples in mathematics, we can induce multiplicative structure of an invariant using the geometric diagonal. For instance, in algebraic geometry, if we have category of motifs, then practically all cohomology theories of interest are equipped with a cyclic class map, which sends intersection products to cup products. So intersection products are related to the diagonal. And if we go to cohomology classes, then we obtain cup products on cohomology theories. And every space in the category of spaces, which is monoidal because we have a Cartesian product, is a comonoid. And the diagonal is a kind of co-multiplication of this set. So the difference between the classical theory and the non-commutative setting is that our objects do not have this comonoid structure. Okay, which means that this multiplication in the corresponding sister algebra is not an algebra map. Okay, in the category of spectra, which is also monoidal, every suspension spectrum obtained from a given space by iterating suspensions also is automatically a comonoid. So this explains why all these theories in the classical setting are equipped with a natural multiplicative structure. So we are looking for some replacement for this. And the idea is that although we do not have a diagonal, we have something which is a kind of a diagonal. Namely, diagonal is a simplest equivalence relation. It means that we can speak about 2 points which coincide. In the non-commutative setting, we have to abandon this strict way of speaking about equality of points. First of all, because we do not have points in general. But we can replace the diagonal by some kind of thickened diagonal when instead of the identity relation, we can speak at once about different relations, like groupoids, like some categories. And then if we blow up this diagonal to something which can be written in terms of some groupoids, then we can speak about a kind of a generalized or thickened diagonal. Why this multiplicative structure is important and what is the motivation for our effort is that, for instance, what was not able to be distinguished by K groups can be distinguished by K rings. If you remember this example about complex projective spaces and n+1 point spaces, which were identified in K theory as because they were KK equivalent. If we use the cup product on K theory, then we obtain for these spaces completely different rings. For instance, the K ring of CPN contains lots of nilpotents, and K theory ring of n+1 point space is simply a product of copies of Z. There are other problems in geometry or in topology when using cup products, we can, for instance, show non-existence of some maps. Like, for instance, for n greater than 1, there is no retraction of CPN to its complex projective hyperplane. Okay, this can be proven using only the multiplicative structure of K theory. Okay, there is one problem with this cup products. If you remember the notion of K equivalence, for classical spaces, K equivalence induced an isomorphism of K rings because this structure was related to something which was described in terms of maps between spaces. But if we replace maps by correspondences, the situation is very complicated and very interesting. For instance, in the category of motifs, correspondences do not preserve cup products. But sometimes they do not preserve them in a very interesting way. For example, some stratified Mukai flops. So this is the notion of birational geometry, which are known not to preserve cup products, can be corrected. For instance, there are some correction terms which can be expressed in terms of Gromov-Witten invariants, very important invariants of projective varieties, for instance. Another example in classical topology is that is based on the fact that K-theory is an extraordinary cohomology theory. It satisfies all Stinot's axioms except the dimension, the normalization or dimension axiom. Therefore, the Mayer-Wittroy principle applies. But some of the maps in the Mayer-Wittroy's long or six-term exact sequence in K-theory are not algebra maps. They do not respect the cup product. For instance, we have differences of ring homomorphisms, which are not ring homomorphisms themselves. Okay. So you see that even in the classical theory, there are some reasons for considering K-theory, even if it has a multiplicative structure. Sometimes you have to weaken this structure from a ring to an abelian group. And this suggests the following replacement of a multiplicative Z2-graded ring structure of the classical K-theory. And the definition is following. We introduced the notion of so-called Z2-graded co-augmented module. So it's a triple consisting of a ring, Z2-graded unital ring, a module over this ring, which is Z2-graded over this Z2-graded.
Sorry, I think that there is a question on chat.
Yes. I cannot see because I'm in the, let me see. Okay, I have here.
The question is about the existing.
Regarding non-retract of CPN, is not singular cohomology sufficient to proving this? We no need to K-theory. Of course it is true. And the proof with use of this singular cohomology is even easier because the computation is immediate because we have this Z grading. But it is still interesting that the same argument works by the K-theoretical arguments when instead of Z grading, we have only Z2 grading. Okay. By the way, we are not so much interested in this singular cohomology because we don't know how to generalize it to the non-commutative setting. Okay. So in a sense, K-theory is the only invariant for which there is at least a chance to be extended to this non-commutative setting and possess something like a multiplicative structure. For instance, you could say that cyclic homology is a kind of such an invariant, but up to my knowledge, I don't know any successful result of extending to cyclic homology the cup product. So that's the problem. But I'm going to show that if we think about K-theory, the situation is much better. So maybe it could suggest some idea which could also work in the case of cyclic homology. But I'm not sure. Okay, thank you for the question. Okay, so what is this candidate for this multiplicative structure? So since sometimes we regard this K-theory as a ring valued invariant, sometimes we are forced, even in the classical setting, to regard it as abelian group valued invariant. We are introducing some new notion of co-augmented module consisting of a ring, a module over this ring, and a distinguished element in this module, which is in degree 0, which is even. Okay? And such co-augmented modules form a category. Morphism between such co-augmented modules consists of a Z2 graded ring map between these rings corresponding to this co-augmented module, a unitary Z2 graded module map over this ring in the domain of this ring homomorphism. And we assume that this module map transforms this distinguished element of one to the distinguished element of the other. So this is a very simple object. And I hope you understand.
What is this co-augmentation? Why do you call it co-augmented?
Because there is a distinguished element in this module.
One.
Yes, for some purpose, I'm denoting this as one. But in the case of K-theory, if you have an abelian group, so the abelian structure is not the only structure, natural structure of this invariant, because we have always a free module of rank 1, and its class defines a distinguished element in the K group, usually different from 0, of course. Okay. So already
yes.
because yes, please.
If you have unital algebra, so the fact that the algebra is unital is equivalent to the existence of the map from C to this algebra, yes? And this is always the case.
Yes.
And if there is a map going in the opposite way, you are saying that your algebra is augmented, yes? So this
No. I'm saying that my module is co-augmented.
No, but I'm saying in general, so this definition is something in the spirit going the other way around, yes?
No. It is not we are not interested in augmented algebras. So even unit of the ring is a kind of co-augmentation. It's a distinguished element of the group ring. We are not talking about any dual situation. Okay?
Yes, but this explains the notation, yes, the notation and also the terminology. I was only addressing this issue.
But it has nothing to do with this dual augmented point of view. So augmentation on a ring is something like a point. This co-augmentation is something like a constant map from a space. Okay?
Okay, thank you.
So we have the category in which we expect our invariant, multiplicative invariant will take values. Okay? So please know that when I speak about a module, so I understand by this a package. It's a module together with the ring of coefficients. Okay, So therefore, it is a multiplicative structure. We have a multiplication in the ring, and we have a multiplication of a module by elements of the module by elements of this ring of coefficients. Moreover, which is not written on this page, if we have this distinguished element, then multiplication of this distinguished element by elements of this ring defines a canonical map from this ring to this module. Okay, which is not always so in the situation of a not co-augmented module. Okay. So the first question one could ask is how this category of co-augmented modules is related to the category of rings.
Tomek, can I ask you?
Yes, please.
It's Ludwig. Hi.
Hi.
But looking on this, let's say, properties axioms, you don't see any, I mean, what is the role of this one? Can it be just zero element of the module?
It depends. Sometimes even in the ring, unit is equal to zero for a zero ring. So some degenerate situations are allowed.
Okay.
But you see the relation just on this slide. This is a theorem saying what is the relation. If we replace rings by some other multiplicative objects, then we see that that between these two categories there are some functors. So first of all, we have a functor from rings to co-augmented modules, which puts the ring itself as a module, and the distinguished element of this module is simply the unit of this ring. Okay? So this is the obvious functor from rings to modules. And this turns out to be a full embedding. Moreover, a second of reflection allows us to realize that that this full embedding functor admits a left adjoint. And in such a situation, when we have a full embedding admitting a left adjoint, then we have then we see then we say that this full embedding is a reflection. Okay, and the reflector is this left adjoint. In this case, it's something very easy. Simply forgetting about this module and with this distinguished element part, and remain and only this ring remains. Okay. In such a situation, we see that these rings it's a reflective subcategory of the category of co-augmented modules. And this situation, this relation between two categories resembles something. For instance, commutative algebra, the category of commutative algebras is reflective in associative algebras. Okay, and the reflector is commutativization. So we see that since we want to extend multiplicative K-theory from classical spaces to quantum spaces, it's a very natural relationship between the categories of these recipients of these invariants. So this is expected. This should be so. Otherwise, this generalization would have no meaning. Would be meaningless. Okay, there is another functor relating these two categories, namely, I can not this category, sorry, the category of co-augmented modules and the category of abelian Z2-graded groups, namely having a triple Rm and this unit element. We can forget about this R and forget about this distinguished element of this module. and even we can forget about this module structure, and then we can regard this M as a plain abelian group, Z2 abelian group. Okay, and there is a relation between this full embedding of rings into co-augmented modules and this functor, namely, we have a commutative diagram, commutative triangle. This vertical one, vertical arrow, hook arrow, is this full embedding. This bottom arrow is this functor from the definition above, and this functor from rings to abelian groups is simply forgetting the ring structure. Okay. Go. And then we see how for classical spaces we can make easily K-theory to be a functor taking values in co-augmented modules. We are going from X to the K ring of this X. Next, K group of this X, and the distinguished element is simply the class of the unit of this ring. It's precisely the unit of this ring. Okay.
So Ludwig, now you have the answer to your question. You ask what is the role of this 1 in M, 1M.
In this example.
Yeah.
For classical spaces, when this module is nothing but the ring itself, the unit of this ring serves as an example.
Tomek, so can I ask another simple question? So if you have two non-abelian algebras, you consider, and when you consider multiplication in non-abelian, non-commutative algebra, of course, it's not a homomorphism from tensor product to algebra, but you say that it still has some additional structure when you view this as a module over the algebra itself. That's what you want to say, more or less, yeah? That the multiplication map, which is not a homomorphism.
X is classical. It's a space.
No, okay, but in general, to your, I mean, I'm just interested in this diagonal map. So if you have multiplication in non-commutative algebra, still it has some additional structures besides being multiplication. It has, if you treat this tensor A as a module, then it's a module map in your sense. Probably that's what you want to say.
No, this idea is different. So the idea is not to change this abelian group corresponding to this invariant. Okay. The idea is to provide a ring part, to make it a triple. Okay?
Mm-hmm. Okay, I understand.
So for classical spaces, such a construction is so trivial that one could ask, so why we should be interested in this? Okay, because this triple datum is entirely equivalent to the K-ring functor. So nothing new we obtain for classical spaces.
Okay, I will ask you at the end. Okay, thanks.
But the justification of our approach is the following theorem. So this theorem is like this. So there exists a full embedding Q, like quantization, something like extension to quantum spaces, of CW Walhausen categories, which Piotr introduced in the previous part, and a functor K such that the following diagram commutes. But what do we have in this diagram? So we have the category of compact Hausdorff spaces, the category of Z2 graded rings, and the usual K theory as this functor K. we have this full embedding of compact Hausdorff spaces into the category which is opposite of the category of unital sister algebras equipped with some additional data, which will be defined soon. This category will be equipped with a functor K to augmented modules, co-augmented modules, making this diagram commute. The cofibrations of both Waldhausen structures are monomorphisms, and weak equivalences are K equivalences. Okay. Moreover, before I say the last point, I have to stress that at this moment, you could think about completely trivial ways of completing this black part of this diagram to a commutative square. So if there are no conditions for this functor K below, and for this category K compact quantum spaces, it would be some kind of cheating, because you could say that this category coincides with the category of compact Hausdorff spaces, and all your quantum spaces of your interest are classical spaces. Okay, but the third point makes this theorem completely non-trivial. Namely, there's a condition that the composition of this red K with this functor from co-augmented modules to abelian Z to great abelian groups factors through K theory of unital sister algebras. Okay, so this relates this construction with K theory of in general non-commutative sister algebras. Okay, so what is this about? So I have some remainder about these Waldhausen categories. So we start from unpointed Waldhausen categories. If somebody is used to Waldhausen categories from algebraic topology, then I have to recall you the fact that Waldhausen introduced a pointed version of our definition. But since quantum spaces usually do not have points, they are not pointed spaces, or even if they have these points, these points are so rigid inside these non-commutative spaces, then that topology based on pointed spaces cannot be extended to non-commutative setting. Therefore, we are forced to consider this unpointed version. And according to Waldhausen, it consists of two classes of morphisms. Oh, sorry, I forgot that this pointed Waldhausen category is something where the initial object is equal to the terminal object, and this is a singleton space in both cases. But now we have to separate the role of the initial object, which is denoted here as an empty set, and the terminal object is a singleton space. Okay. So this unpointed Waldhausen have these two objects separated, and we have two classes of maps: cofibrations depicted as hook arrows, and weak equivalences depicted as arrows with this equivalence sign, satisfying some axioms. So first three axioms are about cofibrations, all isomorphisms and composition of cofibrations are cofibrations. For any object, the unique morphism from the initial object to X is like an embedding of an empty space into our space. It's a cofibration. if we have a cofibration from X to Y, and we have any morphism from X to X tilde, then the push out of this cofibration along an arbitrary map is still a cofibration. For these weak equivalences, we also have three axioms. So first of all isomorphisms are weak equivalences. Weak equivalences are closed under composition. And we have a very important axiom gluing for weak equivalences. Okay. So, this gluing for weak equivalences axiom, in fact, in the business in the setting of non-commutative theta algebras, was noticed by Piotr and others, this was the first axiom which I realized is a part of this much richer structure of Waldhausen categories. So this very important and very useful principle of gluing weak equivalences makes this theory applicable in the case of spaces, even quantum spaces, which are glued from pieces. Sorry, something is happening to my. Okay. Among these unpointed Waldhausen categories, we propose to distinguish some very nice class. So these are categories in which, to objects of which we can apply Meyer-Vietoris principle, in fact. So although classical Waldhausen categories were invented for K-theoretical considerations, for creating some generalized K-theories, this axiom is not a part of the classical Waldhausen's approach. So from this point, we are speaking about something new. And what is the nice feature of this CW Waldhausen categories is that inside these categories we can speak about cofibrations, kind of cofibrations, which are defined up to inverting weak equivalences. Okay. So the calculus of such compositions of the inverse of a weak equivalence with a cofibration inside of the category, so-called homotopy category of this CW Waldhausen category, which means that we formally invert these weak equivalences. The gain from this structure is that these weak cofibrations, which can be represented by cospans, as you see on the screen, which can be composed in a very controllable way. I have to warn you that if you have a category and if you distinguish some class of morphisms, which is called the multiplicative class, which means that identities or isomorphisms belong to this class, and the composition of two also belongs to this class, then you can always create a category which has a universal property with respect to inverting of a given class, of multiplicative class of morphisms. And this is called a localization with respect to this class. But if you do not impose some stricter conditions on this inverting, then in general you cannot say even whether your resulting homotopy category is non-trivial. Because if you do not control this inversions, you can contract everything in this category, in principle. So people invented some way of protection against this pathology, and this is called the left fraction calculus. Namely, the controllable way of composing such weak morphisms consists of composing spans cospans for the price of adding to the concatenation of two some push out. So if we want to compose such two, let's say, roofs, then we have to complete the concatenation of them by this diagram in the middle, okay? And by the universal property of the push out, you have two new maps, J tilde and H tilde here, which can be used in the composition to define this composition of these two roofs, okay? So this is the main gain from this additional axiom, but not only one. Okay, so now let's speak about compact quantum spaces. So for us, compact quantum spaces, it's a category which is defined to be the opposite of the category of unital sister algebras. And we have unital star homomorphisms as opposite morphisms in this category. We have an initial object, which is the zero sister algebra. We have complex numbers, the ring of or field of complex numbers as a terminal object. Surjective unital star homomorphisms are cofibrations, and unital star homomorphisms inducing an isomorphism on K-theory are weak equivalences. Okay. Then, taking these cofibrations and these weak equivalences and these initial and terminal objects, it turns out that this compact quantum spaces is an example of a CW Waldhausen category. Okay, so this means that we can speak about K-theory in the sense of Waldhausen, but we can compute this K-theory using the wealth of Mayer-Vietors principle. Okay. So since compact Hausdorff spaces is a full subcategory in this category of quantum compact spaces, and these cofibrations and weak equivalences are inherited from the same kind of invariant on the level of these compact quantum spaces, we have an analogical theorem for compact Hausdorff spaces. Okay. Moreover, these two categories are related by some reflection. So this category of compact Hausdorff spaces is a reflexive full CW Waldhausen subcategory in compact quantum spaces. Okay, so essentially it's an enhancement of the Gelfand-Naimark duality. So it's so what we say in addition to the Gelfand-Naimark dualities is that these two CW Waldhausen category structures coincide, or maybe not coincide. The CW Waldhausen structure of this ambient category restricts to the full subcategory, reflexive subcategory. Okay,
And this reflection is again commutatization?
Yes, yes, it is commutativization, yes. Or in the language of compact spaces, it's a subspace of classical points.
Yeah, sure.
Yeah,
sure.
Okay. So now we get to the main point of our generalization. It's about creating this generalized kind of diagonal. Okay. And this diagonal is much more complicated than in the classical setting, when simply by the diagonal we understand simply this trivial equivalence relation. So now we have to replace this trivial equivalence relation by some groupoids. They are action groupoids of some quantum groups on some bundles over the space. Okay, so this action groupoid structure is some kind of making this diagonal thicker. Okay, so in the diagonal you have the arrows. Of course, the diagonal is a very simple groupoid, because the only arrows correspond to identities. So in this quantum version, we do not have this identity relation between points. Instead, we have some dynamical identification of points, in this case defined by introducing some groupoid actions, some groupoid action, action groupoids for some compact quantum principal bundles over our space. Okay, so the main point is that we can organize this kind of thickening of the diagonal in something which resembles topology. So introduce the notion of K-topology. So first we have to define the notion of a K-covering. So a covering family. A K-covering family of a quantum compact space X is a compact quantum principal bundle, which is a pair consisting of a compact quantum group G and a morphism of two compact quantum spaces from E to X, satisfying dually some axiom, Elwood axiom, which means that the action of this compact quantum group on this total space E is free. Okay, and having the notion of a K-covering family, we can define K-topology. A K-topology on X is a collection of K-covering families. Okay, I don't want to say at this moment that it's a collection of compact quantum principal bundles, because this language is a language in which Grothendieck defines his kind of generalization of topology. So first we have covering families, and K-topology is a collection of covering families.
But I have a question, Tomek.
Yes.
So you say that a K-covering family is just a compact quantum principal bundle.
Yes.
So does it mean that the family has just one member? That's a very poor family.
Yes, but topology is a family of families. But now it is a family of compact quantum principal bundles.
But why call it a family if it's just one element?
It's a standard terminology in generalized topology.
Mm-hmm.
Okay, it's a language of Grothendieck and others. Okay, so there is some reason to say that the principal bundle is a covering family, because in generalized topology, such like faithfully flat topology in algebraic geometry, sometimes this covering family contains only one morphism, and usually if you have many morphisms in some good category, you can create a single map from a family. You simply have to take a coproduct of members of this family. If this coproduct in this category exists, then this map from this coproduct to space X is the same as the collection of maps from these members of this family to X. Okay? So to say that it's a family, so the cardinality of this family is something which is irrelevant in good categories. Okay. Okay, and when equipped with a K topology, a quantum space would be called K compact quantum space. Okay. So this is a very delicate point, because from the point of view of classical topology, there is no need for this additional datum, which is kind of K covering K topology. I will explain it in a minute. But in the non-commutative setting, it seems that the structure of a C-star algebra doesn't contain all topological information of a quantum space, in a sense. So I mean by this that kind of topology for which we can speak about classical constructions for quantum spaces is not entirely encoded in the structure of a C-star algebra. Why topology is important? Topology is important because it makes the spaces related by special maps. Not everything is allowed, like in set theory, for instance, among topological spaces. We have only continuous maps. So in this situation, we also can define continuous maps, kind of continuous maps, which I call K continuous maps. And the definition is slightly convolved, but if you think about the definition of K continuous map, you can easily recognize what parts of this very long definition correspond to what parts of the classical definition. Okay, so we call a morphism of quantum compact spaces from X prime to X equipped with K topology, K continuous or K continuous map, if for any compact principal bundle over X belonging to K topology on X, there exists a compact principal bundle G prime, E prime, X prime over X prime belonging to the K topology on X prime, a morphism of compact quantum groups from G prime to G, and a morphism of quantum compact G spaces from E prime to E. Okay, so the homomorphism of this morphism of compact quantum groups from G prime to G makes both spaces, E prime and E, G prime spaces. And then we assume that there is a map which is from E prime to E, which is G prime equivariant. Okay, and everything about compact principal bundles, compact quantum groups can be written equivalently in terms of so-called Peter-Weyl algebras. So instead of compact quantum groups, we can speak about Hopf algebras. Instead of compact quantum principal bundles, we can speak about Hopf-Galois extensions. Okay, And in this language, what I wrote in a way we do in topology, everything dualizes to respective algebras, and we have vertical Hofgala extensions, and these two maps, alpha and beta, are maps between the bases, the algebras of functions on the bases, and alpha corresponds to the map between total spaces of these principal bundles.
So alpha is equivariant, right?
Alpha is G prime equivariant. So we have two principal bundles with two structural groups, let's say, but we have a group homomorphism, making both G spaces, G prime spaces, okay, in a sense.
And could you give an example of a morphism of compact quantum spaces which is not K-continuous?
Yes, of course. Okay, so let me explain. Because
okay, but we haven't finished the sentence, satisfying the conditions.
Yes, yes. So please wait to.
Sorry, yes.
So this slide is too short. I warned you that this definition is quite long, and it is related to your question precisely, because there must be some condition fulfilled, some additional condition, which can be written in terms of some generalized canonical map. If you remember the canonical map from the theory of Hofgala extensions, then you see that this canonical map can be generalized to something similar. And it is even written in terms of a very similar formula. Okay? And the condition which this diagram should satisfy is the bijectivity of this canonical map related to this diagram. Okay? So in a sense, this condition means, classically, it would mean that this diagram is a pullback of principal bundle. Okay. And because if you have a pullback of the principal bundle from X to X prime, let's say, then you can induce on this pullback a structure of a G prime principal. Sorry. You can, if you have a pullback of a G principal bundle over X to another base, which is denoted by X prime, then you obtain some G principal bundle over X prime. But our E prime over X prime has a different structural group. It is G prime. Okay. But you can change the group by taking the, let me try. Can I use this? If we have, oh no, my pen doesn't work here. I don't know how to activate my pen on this. So I will explain it like this. So we have G prime principal bundle, and we have the pullback of G principal bundle from X, both over the base X prime. And then if we change the structural group by extending the structural group on this E prime from G prime to G, then we can compare these two G prime principal, G principal bundles over X prime. And in the classical situation, this comparison is an isomorphism of G principal bundles over X prime. Okay. So what I wrote in terms of algebras is precisely equivalent classically to this condition. So that's the meaning of this condition.
So you are saying that for classical compact Hausdorff topological spaces, any continuous map is K continuous.
Yes, yes. So this is the in this remark below. Because So the point is that So let me read this first. Before this remark, let me come back to this theorem. So K topological compact quantum spaces with K continuous morphisms form a subcategory K compact quantum of compact quantum spaces. Okay, and this remark says that since classically any G equivalent continuous map of G principal bundles over the same base is an isomorphism, while any continuous map between bases pulls back principal bundles and lifts to an equivalent maps of principal bundles. And now what you said, every continuous map is K continuous with respect to K topology consisting of all classical compact principal bundles. So even if we decorate classical spaces with arbitrary compact principal bundles, it doesn't change the classical notion of continuity of a map. Okay?
Mm-hmm.
So now we are going to relate this K topology to K theory. And in the context of this remark, one thing about vector bundles over compact Hausdorff spaces is important. Namely, every vector bundle, in fact, is associated with some compact principal bundle.
By the way, Tomasz, before I forget, I mean, in order really to see this condition implemented for classical spaces, well, you do it through sister algebras, but then you cannot plug in sister algebras into these equations or just use the Peter-Weyl functor, right?
Yes, yes.
Okay.
But this algebraic form of this condition classically reads as a commutative diagram of some classical spaces.
Mm-hmm, mm-hmm. Yeah.
So this Peter-Weyl algebra is something which is an analog of a Hopf algebra, which is a dense star Hopf subalgebra of an algebra of continuous function of a compact quantum group. Okay, which is very convenient because we can speak algebraically about topology.
Exactly. Yes.
Okay. So as I started. Okay. So now I have to relate this K topology with K theory. So this little k was a notation which is motivated by this relationship between this K topology and K theory. If you remember this abbreviation CW Waldhausen category, so this small CW also is motivated by usefulness of this CW Waldhausen categories, especially when we consider CW complexes. So what's the situation in K theory? As I started to say, over even more than compact Hausdorff spaces, over every paracompact space, every vector bundle is associated with some principal bundle with a compact structural group. Over compact spaces, it is simply a compact principal bundle over a given compact space. Okay. So even classically, you see that there is a very close relationship between K theory and principal bundles, because K theory is some enhancement of theory of vector bundles, and every vector bundle, in fact, is equivalent classically with its compact principal bundle of is orthonormal frames, okay, or unitar frames if they're complex bundles. Okay, so until I abandon this K-topological part, let me come back to this question of covering families and so on. So there is a weekend.
May I have a question?
Yes, please.
So what you have to assume on your topological space in order to speak about the frame bundle?
Paracompact is enough, because it's a matter of constructing a scalar product. Okay, if you have, you know that your vector bundle is locally trivial, then you can inscribe into this trivializing covering some partition of unity, and using this you can glue some Hermitian product.
Yes. Okay. I see. So you are given your vector bundle at the start. So
yeah.
The context is that you have just a compact, for example, paracompact space. Yes.
Yeah.
But nothing like a manifold, of course.
Okay, exactly. Yeah, because it's not a frame bundle on a manifold. Yes, that's a frame bundle for a vector bundle, which need not be anything like a tangent bundle.
Sure. Yeah. Thank you.
Okay. So, what I start? There's a weekend, but sufficient for speaking about Schiff's version of Grothendieck topology. This simplification consists about forgetting about the Grothendieck's assumption of saturation. So it's one could say it's an unsaturated version of Grothendieck topology, which was introduced by Peter Johnstone, who coined a name for it. He named it coverage. Okay. And we have the following theorem. Families of compact quantum principal bundles together with K-continuous maps form a coverage in the sense of Johnstone. So it's not only an analogy, okay? It is really a topology, sufficiently generalized topology in the classical sense, when in this sense people are using in other subjects in mathematics. Okay, so now we are going from K-topology to multiplicative K-theory. And essentially, I said already, what is this relation between K-topology, which means families of compact principal bundles, and K-theory. So for every compact quantum principal bundle, we can consider a class of associated vector bundles. If we have a representation of a quantum group, let's say finite dimensional representation, okay, then we can construct a vector bundle, non-commutative vector bundle over this quantum base. Of course, everything can be written algebraically. Instead of a vector bundle, we can speak about the module or bimodule of sections of this. And the only difference, if you compare this non-commutative setting of these associated vector bundles with its classical counterpart, is that this time, these associated sections of associated vector bundles are bimodules. And in the classical situation, when everything is commutative, these bimodules are symmetric. So this is the moment when people are speaking about bimodules, but they are calling them modules, because if you have a symmetric bimodule over a commutative ring, then knowing the one-sided structure is enough to recreate the second one, another one, by commutativity of the ring. But in the non-commutative setting, associated vector bundles are not only one-sided modules. Their structure is richer. They are bimodules. But being bimodules, they can act on modules, or, for instance, on section modules of vector bundles, this time maybe not associated, over a compact space. Okay. And given this compact quantum space X, we have also a suspension of this space, because we have well-defined operation of suspension in sister algebras. Okay. So this
Tomek,
is
just a second. I have a question to Francesco, if he's still around.
Mm-hmm.
Yes.
Yes.
Because I think it's worth emphasizing. I think it was you who proved that if you take this powers refill idempotent over the irrational rotation sister algebra, that it cannot be realized as an associated vector bundle for no matter what kind of Hopkal extension you would hook up. Do I remember it correctly?
No, no, it was not me.
But anyway, there's some no-go theorem that says that it is, but unlike in the classical case where every vector bundle is associated to the frame bundle, there is a serious issue with the frame bundle in the non-clear setting. I mean, in general, it does not exist. So it's no longer true that every module, which gives you some, say, non-interesting element in the K-theory of the sister algebra, but every finite projective module can be realized as an associated bimodule for some compact quantum principal bundle. That's simply not true. So this is why when you said, Tomek, that, okay, but these bimodules can now act on modules, that's important because there are some modules which cannot be turned into bimodules.
Yeah, simply, it is more or less obvious that if you have even a bimodule, and if you forget one side of this bimodule over a non-commutative ring, then there is no way to reconstruct it. So bimodules and modules over a non-commutative ring, these are completely different categories of satisfying completely different, having completely different categorical properties. So even looking for situations when by accident we can compare these completely different mathematical things, it would be not appropriate. Okay, so bimodules are in fact operations on modules. So these associated vector bundles are in fact operations on non-commutative vector bundles. Okay. So since we can act by these bimodules on vector bundles, and since these section bimodules of associated vector bundles are both sides, from both sides, assuming that the antipode of the Hopf algebra is invertible, since okay, they are finitely generated projective, then multiplication tensor product by modules is an exact functor, extends to the action of these bimodules on K-theory. Okay, so the idea is to use this action to create some ring acting on K-theory, and take it as this missing ring, which is a part of this triple of this co-augmented module. Okay. So now, since K0 of X contains a class of rank 1 trivial vector bundle, we can define using the suspension and the Bott periodicity, and if convenient, we could use also a reduced version of this construction, which is used to define the products, the capped products classically. So now this can be used also in a sensible way to define the functor from k-topological compact quantum spaces to co-augmented modules, Z2-graded co-augmented modules, which associates with a given k-compact quantum space X, a triple consisting of the ring R, which is built with this associated bimodules, K-theory of this space itself, and the class in K-theory of this rank 1 trivial vector bundle. Okay, so this ring formally is defined as follows. It has, since it's Z2-graded, it has two parts, even and odd. So even part is the inverse limit over all principal bundles from a given k-topology of the quotients of representation ring of this quantum group G modulo the annihilator of this action on the unit element, on this distinguished element in K-theory. Okay, so there's a theorem saying that this the associated vector bundle, in fact, is an image of some functor. This is the strong monoidal functor from the category of representations of this quantum group to the category of this associated bimodules, to the category of bimodules simply. It's a theorem of Schauenburg, if I remember well. Okay. So therefore, we obtain some action of the representation ring of this structural compact quantum group on K-theory, and we are taking the quotient of this representation ring R of G, modulus annihilator over all compact quantum principal bundles belonging to this K topology, and the odd counterpart of this ring is this even part on the suspension on this space. Okay, so classically, K-theory is an extraordinary cohomology theory which can be computed. So the way we can compute K-theory uses usually some Mayer-Vietoris principle, and the most important kind of spaces on which this Mayer-Vietoris principle could be applied is the category of CW complexes. Okay.
Tomek, I do not mean to scare you, but your time is up.
Oh, sorry.
And there's no way you can still give 9 slides. So please think about the way to wind it up.
Okay, so let me do this in this way. So CW complexes are built with boundary maps from spheres to balls, and they are defined by some abstract conditions
in K-theory.
About K-theory. So now we call them K-spheres and K-balls and some boundary maps. Having them, this is the remaining part of these conditions on K-theory of these models, local models from which we can glue our spaces or quantum spaces. We can introduce, first of all, the definition of quantum K-weak CW complex when instead of closed embeddings of one skeleton into another, we have weak cofibrations in the homotopy category of compact quantum spaces. Okay. So every next skeleton arises by gluing some or attaching some cells, which is the push out diagram, which makes sense in our category. Okay, and among these weak things, we can speak about strict quantum CW complexes, when in all weak cofibrations, inverted weak equivalences are identities. Then we can speak about these objects in this homotopy category as objects simply in the initial category of compact quantum spaces. And then we have two examples. One which is strict. It is a theory of Waxman-Soibelman quantum odd spheres, which are acted on by U1 and having quotient quantum complex Warszawski spaces as quotients with respect to its action. And we have multi-Pullback odd spheres and their quotient quantum complex Warszawski spaces. These spheres are sometimes called Haggard spheres. Okay. And using these as building blocks filled with respective balls, we can glue CW complexes. So one structure is strict in the case of Waxman-Soibelman, but in the case of Haggard spheres, we obtain a weak CW complex. And then we can take the classical example when K-theory is computed explicitly by Atiyah and Todd. It's a case of a complex projective space admitting standard filtration by hyperplanes of some codimension, which induces a tower of standard nilpotent ring extensions in K-theory. So these K-theories, multiplicative K-theories or K-theory rings, are simply the rings of truncated polynomials, okay, with standard mappings between them. So these mappings are quotients by lower and lower powers of the generator X. Okay, and then we have the following theorem that in the case of the Waxman-Soibelman quotient complex, quantum complex Warszawski space, which is a strict quantum CW complex with K topology given by the compact U1 principal bundle being the Waxman-Soibelman sphere, and admits a strict K topology of filtration by Skeleta, inducing a tower of standard nilpotent ring extensions in multiplicative K-theory. But now, by multiplicative K-theory, we mean not only ring valued, but K-theory valued in co-augmented modules. And similar theorem we have for this multi-pullback case. And finally, we have a theorem that there is a multiplicative K equivalence from the weak hyperplane filtration of one kind of CPN, one quantization of complex projective space to another. Okay. Moreover, preserving this strict filtration by these hyperplanes. Okay. What is important? Important is that as sister algebras, they are not isomorphic. However, for both, we have almost the same theorem. So how to explain this? Oh, sorry, something. Yeah, so I lost some page. Okay, so the idea is here that although these two quantizations of CPN are not isomorphic, they define the same multiplicative K-theory type. So you know that the quantization is not a unique operation. it's a deformation in arbitrary direction in a sense, but we see that at least in this example, it makes sense to collect all quantizations which are related by some morphisms inducing isomorphism in K-theory. And then we obtain something which is called, which we call multiplicative K-theory type. And we see that the fact that we have the same theorem, almost the same theorem in both cases, can be explained by the fact that these two quantizations belong to the same multiplicative K-theory type. And these, or as such, this can be considered as a quantization of a classical K-theory type of the classical CPN.
And very importantly, this is with multiplicative. We don't just get a stupid abelian group, Z2n plus 1, but we get this beautiful Atiyah-Todd identity.
Yeah, so we do not identify CPN, for instance, with the n plus 1 point space.
Exactly.
Yeah, so that's the point. So we use lots of non-classical methods. We cannot, the only thing which is present in the classical approach is the Meyer-Vittori principle. But in the case of C-star algebras, K-theory is some construction satisfying this Meyer-Vittori principle, but not being a generalized cohomology theory, because Steenrod axioms do not make sense for these quantum spaces. But still, this Meyer-Vittori principle can be used to prove many things. But models of our spaces, which are convenient models to do calculations about our objects, are not classical. We realize our C-star algebras first as graph C-star algebras or étale groupoid C-star algebras. We are using Petel-Weierkopf-Galois extension theory, and we transfer the associated vector bundles via equivariant maps. So these are tools. Crucial. Yeah, so these are tools we are using here. It is quite interesting that these methods cannot be used in the classical case.
Yes.
So we do, because graph C-star algebras representing our spaces do not survive this classical limit. And also this étale groupoid picture also doesn't survive this classical limit. Mm-hmm. Also, converse is true. Namely, classical methods cannot be used in this classical situation, mm-hmm. because Atiyah and Todd very heavily use such things like multiplicativity of this theory. Okay, they are using spectral sequences which are not present in this non-commutative setting. So it's very interesting that this classical limit is highly singular in a sense, because geometric or functional analytic generators, respectively of K-theory and K homology, either degenerate to zero or blow up to infinity. The only thing which is stable under this classical limit is the result of index pairing. This is stable with respect to quantization, yes, under quantization. But everything which is related to geometric or functional analytic realization of generators of these theories does not survive this quantization. Therefore, methods from one field cannot be transferred to another, but still it's quite interesting that results survive to some extent. Yeah. So this is what I wanted to say. Thank you.
Okay, thank you very much, Tomek. So I can draw a smiley face for you. Yeah. Thank you, and let's continue with questions. Any other questions, please? Ludwig, are you happy now, or more questions? You want to ask something later?
Well, I'm happy, yes, but I will ask privately, maybe Tomek, some more explanations. Not now. Okay, thanks,
Okay.
Tomek.
Okay.
So nobody wants to ask a question?
So maybe I have one technical question. When you talk about the metrizable compact outdoors of spaces for KK equivalence, right? You mean that you need the metrizable for the sister algebra to be UCT class?
No, it is separability.
Yeah, but do you need a separable for the sister algebra to be UCT or?
No, I don't think so.
Because then it should be true. So every commutative sister algebra should be. So this means that you don't need really that is a metrizable topological space, right?
The point is that K theory behaves well for separable sister algebras.
Yeah, but still the universal coefficient theorem is for valid for all commutative sister algebras, right?
That's what I believe.
Yes. K theory means KK equivalent.
Yes, I believe so.
Yes, but the point is that universal coefficient theorem uses only part of the structure of KK theory. To have KK theory as a theory of bivariant theory of correspondences between spaces, you must assume this separability.
Okay, thanks.
Anybody else? Well, if not, let me thank Tomek again and for presenting our very long and complicated paper. Let me now stop recording and tell you about our future plans. I stop recording. Thank you, Tomek. Thank you again.